so this is our second to last topic on power plant electrical. We're going to talk about instrumentation systems. Now, the power plant system is always going to have its a few unique instrumentation systems, especially in the turbine world. There's things that on the turbine side of the house that exist that you will not see on the recip side. Now, if you want to know more about some of the more basic engine instrumentation systems, go back to our recip video, and it'll have all kinds of information on that. This video is going to just fill in the gaps of what that video didn't go over, like EPRs and things of that nature that are specifically geared towards the turbine world. All right, so with that, let's get going. Okay, to get it started off, let's talk about engine speed indicating systems. Engine speed is something that's going to be unique on the turbine side that you just generally won't see on the recip.
Okay, so this is the ECAM's display for a Airbus A320. So we want to. I'm just going to orient you to this right fast. On the very bottom, which the section title is covering up, is your indicators that are inside of the inside of the cabin. So you see like seatbelt signs on, no smoking, so on and so forth. You also have a parking brake and landing light indication that's on there. So this guy's probably sitting on the ground waiting to push. And so that's not really what we're worried about today. FOB is fuel on board, so you can see it's Airbus, so they have in kilograms, 4,960. The other side is your flap slat indicator, so they have like flap slat 2. None of that's really what we're after. What we're really after are these middle dials here that you can see. There's 3 on either side. Now, one's on the left is engine 1, and one's on the right or engine 2. All right. Now, starting at the top, you have EPRs, EGT, and then N1, and then percent of N2 on the other side. So, we're going to go over all of these in greater detail here in just a minute. But what I want you to understand is that these are engine speed indications. This tells you what's the fan speed looking like from different angles. So EPRs is going to say like, well, how fast is it going around up front versus how fast is it going around in the back? Like what do those pressures look like of the air coming in and the air going out? EGT is going to be like, what's our exhaust gas temperature look like? That's not going to tell you so much the engine speed as it is the efficiency of the burn that's happening there. Now, you can get it way too hot and you can overcook the engine, and then that has a lot of problems. It can get it way too low, and then you're not producing enough to sustain the burn. Eventually, you're going to have a flame out, and you have to restart the engine before you crash. Now, N2 and N1 is going to tell you a lot of the same things that that EPRs will tell you, except for the fact that N2 and N1 is looking strictly at the rotational speed and or the torque of your compressor inlet versus your compressor outlet, and so it's showing that those two speeds and like how they compare to each other. EPR, your engine pressure ratio, is going to be looking at the air, not just the fan speed. Now, all of these give the pilot a pretty high level of fidelity on the health of those two engines and like what they're doing, and different indications on either one of them will help inform, hey, look, this is what's going on with that engine. More importantly is that like this is also being logged in the diff dial, or Airbus's version of the diff dial, and so that way if there is some sort of problem, you can turn around and download all that information, look at it on a maintenance laptop, and say like, oh, well, hey, look, whenever you get into this point during the flight profile, these things are starting to happen, or we're starting to have these faults, or whatever the thing is, and it helps you as the maintainer be very efficient in your troubleshooting. So that way you can go and take care of problems before they develop into bigger problems.
Torque meters is another one that's a unique turbine concern. We don't care that much about torque on the reciprocating engines. Not that they don't produce it or anything else like that, it's just that we don't use it to guide our decision making from the cockpit.
Okay, torque meters. Torque is a big deal in the turbine world. A torque meter is an instrument that's used to measure the torque or the rotational force in a rotating system, such as a turboprop or turbo shaft engine. So you'll hear, especially in the helicopter world, this becomes a really big deal because they are always looking at main rotor torque versus the engine torque, and so you're wanting to keep the main rotor torque in a certain band, because if it gets below that, you stop producing lift, and the rotor starts to actually produce a lot of drag, and you want to keep the engine torque under a certain limit because you don't want to over torque the engine. And you also want to be making sufficient power, so you want to keep it above a certain range. But that, that's just in turbine helicopters. When you start looking at jets, so for instance, your rotational speed, your N1 on the Learjet, will directly correspond to an NG, which is the rotational speed of the turbine on the back, which will then produce a certain amount of torque. Anyway, so it becomes the primary power output indicator that's delivered by to the propeller or the shaft, helping assess the engine performance and efficiency. Now, how it works is it measures the twist or strain in a rotating shaft using sensors, and then it converts the mechanical torque into a readable signal for display in the cockpit controls. Okay, so it's typically operated by engine oil pressure metered through a valve that's controlled by a helical ring gear that moves in response to applied torque. Not too different than, say, like your altimeter or anything else like that, except for instead of atmospheric pressures, it's using engine oil pressure. This gear moves against the piston that controls the opening valve, which controls the oil pressure flow. The action makes the oil pressure proportional to torque being applied to the propeller shaft. So generally, they've packed the math into that gear ratio, which is pretty intelligent. Generally, the transducer is used to transfer the oil pressure to an electrical signal to be ready on the flight deck, but you can get some of these older analog gears, but nowadays on a modern digital display, it's just going to be a number that comes out. The readout's typically in foot-pounds of torque or percent of horsepower. The torque meter is very important because it's used to set power settings, and the instrument must be calibrated at intervals to assure its accuracy, which will be part of your heavy checks. Generally speaking, you're going to hear torque more often than you will just about anything else out there, because it's generally speaking going to be more accurate than some of the other indicators of power.
Okay, EPRS is another one, the engine pressure ratio. EPRS is another engine indicating metric that is specifically for the turbine world.
Okay, EPRS is the engine pressure ratio. It's the key parameter in all jet engines, be it a turbo shaft, a turbofan, whatever. It's the indicating ratio of the turbine discharge pressure to the compressor inlet pressure. So me, it's saying this is what the air is coming into the engine, and this is the air that's going out of the engine, and how do those two pressures compare to one another. All right, so it measures that pressure ratio of that exhaust gas pressure and at the turbine exit, and the air pressure at the compressor inlet. So means it's looking at the inlet, and it says hey, look, it's at 1 atmosphere, but on the back it's 10 atmospheres. Your EPR ratio is 10. Makes sense? All right, so it's used to gauge the thrust output, particularly in turbojet and turbofan engines, reflecting engine performance. You get it by taking that turbine discharge total pressure, and you simply divide it by the compressor inlet pressure. Now, higher EPRs generally indicate a greater thrust, as it reflects a more efficient compression and expansion. And it's used by the pilots to monitor engine power settings during flight. So they'll pull that. That's kind of almost like, in a lot of ways, it serves the same thing as your RPM gauge whenever you're flying a recip engine. If you're saying hey, look, I want to set at 2,000 RPMs, you might say hey, look, I need to set our pressure ratio up to 20 or 25, or whatever. It's real common in older jet engines and some modern turbofans as a primary performance indicator. However, it does have some limitations. It's less relevant for engines using fan speed. So N1 is your fan speed, generally speaking. N1 will generally replace it as the primary thrust indicator. It's sensitive to environmental conditions like altitude and temperature. So obviously, if it gets cold outside, the air gets more dense, or if you get really high, air is thinner. So this is all going to affect your pressure ratio. So a higher EPR can indicate better thermodynamic efficiency, but design and operating conditions matter. So that is EPR. You'll generally see this referred to in flight manuals. Generally speaking, unless somebody's got a write-up that reflects this, we won't mess with this too much, except for dealing with the pickups primarily. They'll go out. You'll end up having like some kind of crazy ratio that everyone knows is not right, and it's typically going to be wiring or instrumentation somewhere along the way.
Finally, let's look at FADEC one more time. The full authority digital engine control.
Okay, so FADEC, it's an electronic system that controls all aspects of the engine's aircraft performance, commonly used in most your 737s, all your modern jets use FADEC these days. Now, it's a digital computer system that fully manages the entire operation of the engine, including fuel flow, thrust settings, critical parameters. It replaces all mechanical or manual control inputs. Now, it does this for the purpose of optimizing engine performance, maximizing fuel efficiency, reduces the pilot workload. You can even have auto throttles on this, where the throttles will take care of themselves, and ensure safe operations within engine limits. It is super nice to operate an engine with FADEC versus an old hydromechanical unit. I remember when we went from the Indian model of the OH-58, which was a hydromechanical unit, to a FADEC model with the Romeos, and it was a night and day difference. Like whenever you were running the OH-58 back in the day, you had to like motor up to a certain degree, hit the starter, induce fuel, and then keep it going. And you had to watch your EGT, make sure you didn't you don't want to hung start, and you also don't want to hot start the engine. Whereas with FADEC, is like once you got it up to a certain NG, you flipped a switch, and it just kind of took care of the rest for you for the most part. You just had to roll up the throttle to over 90% torque, and you were good. Then same thing with the 737. They make a big deal of being engine run qualified, but really the engine run qualification is just like a question of like what happens if X, Y, or Z were to go wrong, because the actual running of the engine is pretty straightforward, pretty simple, thanks to FADEC. You simply just turn a knob, flip a switch, and then just watch everything kind of come alive, and then at that point you're just managing the engine so that way nothing goes into them or you don't hurt anybody else. It's all because FADEC. FADEC basically runs everything. It's a lot like starting your car these days, whereas like the old days you'd have to sit there and you might be cold, like with your naturally aspirated engines, and you would crank it, and like you'd kick off, and you'd have to let it warm up and all this other good stuff. And nowadays, like I can sit down in my wife's car, put my foot on the brake, and then hit a button, and then the car does everything for you. That's kind of like almost like a FADEC-like system for the for the car. Except for with FADEC, it controls everything for the entirety of the flight, whereas my wife's start button will just simply start the car, and that's it. Its components: you'll have a engine control unit, which is basically just a core computer that basically monitors everything and makes decisions based on what the pilot's wanting to do. It has sensors, so like your N1, N2, EGT, fuel flow, all these things that we're talking about are all feed into that engine control, the ECU or the EEC, depending on manufacturer. And then it has small actuators all over the engine that help adjust components like fuel flow valves, variable stator vanes, bleed valves, all those types of things. The FADEC will automatically regulate fuel flow and maintain a desired thrust. So if you'll set the throttle on a certain position, it will maintain that thrust based on or via all these different pickups, sensors, and actuators to actually make it happen. It protects against overspeed, over temperature, all those old school problems that we used to have. We don't have to worry about anymore because the FADEC simply won't let you do it. It helps manage the start, shutdown, transient conditions like acceleration, deceleration. Like I said, like you can even set up auto throttle on this thing along with autopilot, and the plane will literally basically land itself. It'll fly straight down to the ground. It provides diagnostic data via ECAMs and helps monitor all the problems that happen with the engine, so you can come with a maintenance laptop and just download it and then start troubleshooting. Now, this reduces the pilot workload, and honestly, it reduces the maintainer workload as well, because you don't have to run and guess. It improves safety by preventing operation outside of certified limits, enhances precision engine control, it improves efficiency, and it also reduces wear because you don't have any of the weird human factors that factor into it. The engine's going to run the exact same way every single time, and that way has been optimized to maximize engine life. Each engine is going to have its own FADEC, so you'll see this like channel A, channel B kind of thing. You won't you'll be able to completely control the one engine off of its own FADEC. Now it does have its limitations. It's relying on electrical power primarily. That's one of the big kind of scary bits, and that's why there's like the RAT, there's TRUs, there's all these different ways to maintain electrical power to the engine. Because if you lose the engine, you start losing like all systems. Like that becomes like kind of like the center of gravity that just falls apart. If we lose both engines and the APU, then you're on battery power or the RAT's power alone. It's also complex, and so that means that there's a lot of little gaps in its abilities, and so you have to keep that in mind as you're flying along, that you need to make sure that the software is up to date, that like it's maintained. There's also these new kind of concerns on what happens if it gets a computer virus. Let's say kind of like the classic example that was briefed to me whenever I went on to the tanker program is that there was a guy that had malware on his computer, and then he had a Garmin watch. He syncs his Garmin watch up to it. And then also the malware makes it onto his watch. Well, because his Garmin watch could Bluetooth, it basically transmitted over to an engine of a undisclosed aircraft, and that allowed for that malware to get on that engine and start shutting it down in flight. And so that's a thing to worry about in the future, and you'll see probably more like IT-like operations going on the aircraft. So, for instance, like the tanker. Well, I don't know if I can quite put that on the internet, but there are systems in place to keep that from happening on modern jets these days, and you'll start to see that more and more on the civilian side, where they have like network switches and that sort of thing for anything that plugs up to the aircraft, that you have to have a solid handshake to allow it to talk to the system, so that way we can make sure that no viruses get on board. Anyways, there's also the possibility of kind of like ghost in the machine, like so you have like amber ECAM alerts may indicate issues like sensor failures or communication errors, and then that starts to you can start to see that like the system will trick itself, or it'll believe that there's a failure when there's not a failure, or you simply have actual failures, like sensors will go out, and that will then cause this cascade of problems. We had in the OH-58 world, there was a rash of crashes due to FADEC, that like in a certain flight profile, it would basically roll the throttle down, and because it's a helicopter flying close to the ground, you couldn't recover from it fast enough. And so there are those one-offs that end up happening. Now, generally speaking, they get fixed pretty quickly because they are pretty terrifying. But you could have those typical kind of computer-ish faults that you'd have with any computer, except for this one's flying, and so it becomes a little bit more dramatic. But it does have a lot of advantages. It is far more efficient. It's far more optimized for long-term use. It also simplifies engine operation, makes it super easy to do things. So like whenever, like that's why you have like go around buttons on your throttles these days. You can hit the go around button, and the FADEC knows exactly what that means, and then immediately starts to execute a series of tasks to give you the most amount of power in the quickest amount of time. And it also provides real-time diagnostics, so like you can sit there and watch what the engine's doing, so that way you know exactly what's going on. But that's FADEC, and it is the cornerstone engine management system these days for all turbine engines.